Okay, so good evening, everyone. Welcome to week 4 of the Fundamentals of Nano and Quantum Photonics course, which is offered on NPTEL. And the course instructor is Professor Naresh K. Imani from IIT Hyderabad. So I'm Shazan Bhatt, and I'm a direct PhD student at Electrical Engineering Department, both at IIT Bombay and TU Berlin. So today we are going to see a new topic altogether, which is related to some of the topics we have covered in the previous session, maybe week 2 or week 1. So today we are going to cover plasmonics. Mostly it will be related to plasmonics. What is a plasmon? What is a surface plasmon? And we're briefly going to talk about the electromagnetic wave scattering. What happens to the electromagnetic wave when it interacts with the, let's say, a nanoparticle or a nano scale systems. Okay, we are going to talk about how we can tune those surface plasmon resonances in different systems. Then we are going to talk about surface plasmon polaritons. We're going to talk about their dispersion diagram, which is very important in understanding what frequencies are allowed in a particular system and what frequencies are not allowed. Then we are going to talk about how we can basically excite those surface plasmon polaritons as well as surface plasmons in a, let's say, a nanoscale metallic system or a thin film of the metal. And we are going to see different geometries. So these are the references which you can follow, and most of it are basically the most of the stuff is taught from these references even. This introduction to nanophotonics. Then you can also see optical metamaterials, and there is one more book called as I guess it's called as B.S. Saleh. I guess the name is Introduction to Photonics, and it covers a lot of topics of the photonics. It has approximately, I don't remember, 25 to 30 chapters, but they are small chapters, and they are very concisely written in order to make you understand different topics, starting from the electromagnetic waves, Maxwell's equation, and going into some deeper topics like these plasmonics and metamaterials. So you can also check one of these books. Okay, so I can see that nobody is in the meeting, so I'm going to just record this session, and you guys can have a look on this. You guys can have a look on the YouTube. And the fundamental thing is that basically we have 2 hours in this particular session. So 1 hour I'll try to revise most of the concepts which the professor has tried to cover in this particular week. I guess there were 7 lectures. So the number of lectures were 7. So I'll try to cover most important things in these in this 1 hour because due to the time limitation, obviously. And the next 1 hour, or maybe even this can be 30 minutes, and this can be 30 minutes, and this can extend to 1/2 hour more. This can extend to half hour more, depending upon how much we are able to cover. Because for the question and answer sessions, it only takes half an hour or 40 minutes to solve them. Okay, so we will be trying to solve the questions. Okay, then we'll see how much time it is going to take. This is the rough strategy I have been trying to follow in the most of the sessions that I take. Okay, so we are going to start with the, let's say, for example, scattering first of all. Scattering of electromagnetic wave. Okay, so let me just there is some issue. Let me just disconnect here and stay connected on the one of these systems. Okay, so first of all, we talk about in the lecture 1 of the professors of this week. In the lecture of the week 4, if we talk about lecture 1, the things that are covered is basically scattering of electromagnetic radiation. And we are definitely going to talk about plasmons. And in the week 1, I have talked about different quasi-particles. What are those quasi-particles? These are the particles which are mediating, which are force mediating particles between two. actual particles. So these are not actual particles, these are basically fields which are being quantized in order to get those particles. That's why they have been named quasi-particles. So plasmon is like a excitation, collective excitation of electrons and its coupling with the photons. Coupling, I don't know why is it behaving weirdly, and it's coupling with the photons. So it happens because in a metallic system particularly, there are so many free electrons that they can couple at some particular frequency, let's say omega dash, let's name it omega dash, and you can collectively excite the oscillations in this metallic system and they can just propagate in certain direction. And that is basically what these plasmons are. And then the name basically plasmons has been basically taken from, obviously it's from the plasma. Plasma is basically highly dense, I should say, electrons present, highly dense electrons. The you can also call as huge number of electron hole pairs as highly dense electron hole plasma, but that is what the name has been. That's where the name has been derived from. I know what why this is behaving weirdly. Okay, so plasma includes huge density of electrons per centimeter, let's say per centimeter cube or per meter cube per volume. So once that gets excited, it propagates in certain direction. And then if, because this is propagating just like a wave, you can quantize it. That is what you are going to see in the final lectures. And once you quantize it, you get a quasi-particle called as plasmon. So you treat it like a particle quantum mechanically, you treat it like a particle. And then you have basically you think like that it's just like a particle that is moving from this direction to this direction as if it's like a particle. Okay, that is the story with all of these, most of these ons, like I told you, the photon, the, let's say, the polaron, the phonon. These are the basically the second quantized version, or these are the quasi particles, which are basically the fields which mediate the force between the two actual particles. Okay, so if we talk about now what basically we have covered, we have talked about the atomic polarization in the previous sessions. We know that the atomic polarization is basically something like E square by m 1 over omega naught square minus omega square minus I gamma omega times the electric field of the light. And this is the atomic polarization. And basically the polarizability sum alpha times E. Well, basically the entire terms can be understood by this thing. So what this tells us is that if omega is equivalent to omega naught, so the p value increases to a large value. So the p increases to a large value. Okay, that means this is the condition of what you call as resonance condition. So you have the resonance condition in the system. That is what basically we have covered. Now, we covered one more thing, is that how in the, let's say, for example, Lorentz oscillator model, you treated the electron as a particle, and then there is a nucleus, and there is just like a spring. It's just like a spring connected to it. And once the electromagnetic wave comes in, it starts to oscillate. It gets extended and it gets either compressed. And depending upon the restoring force, let's say F equals to minus kx type restoring force, you wrote a force equation which consists of some damping parameter gamma, which is the damping parameter. And there you have the uh, forcing term on the right hand side of that differential equation, which is basically the electric field, E charge times the electric field, which is basically the electric force because of the electromagnetic wave. That is what we have covered. Now, what happens in these systems is that we also talked about that if incoming electromagnetic wave comes, then it can basically oscillate this positive and negative charge. So it can basically oscillate back and forth. And once it oscillates, it emits electromagnetic radiation. It radiates basically. So once it oscillates in basically oscillates at the frequency of light. Okay, that couples with this particular system. So it starts to radiate, and that means basically it scatters the radiation. So that is the fundamental concept, and it is just like as if it acts like a dipole antenna now. So the dipole antenna, just like, for example, your mobile phone antenna has, let's say, electrons in it, and they are being sloshed back and forth. Once they slosh back and forth, they give rise to electromagnetic waves. Okay, that is how your mobile antenna works. And at some particular frequency, they are being sloshed back and forth, being oscillated, and they emit the electromagnetic waves. That is a similar phenomena here happening. So for the dipole antenna, you know the radiation pattern is something like this. The radiation pattern is like it goes symmetrically in a spherical symmetry. It goes in all the directions, but in a it's like perpendicular to the dipole direction. So actually the oscillations are in this plane, in this direction, but the radiation is going perpendicular to it, just like in this direction. So it's perpendicular to the dipole direction. Okay, so that is it. That's about it. Now we talked about one more thing is that, let's say for example, we can add some more pages. Add page. And one more page, one more. Now what we talked about is if we do some calculation, you can just find it in the book. You can find basically the intensity of the scattered electromagnetic wave by the dipole, or intensity of the scattered radiation by the dipole. And that is basically given by equation p square omega to the power 4 32 pi square epsilon naught c cube r square sine square theta. It's just like a relation you can get from solving some of the simple equations. Basically, intensity is directly proportional to the electric field square. I don't know why it's behaving weirdly today. Intensity is proportional to the electric field square, and once you know other things, you can basically compute it. So using, for example, using the value of P, where this P is this thing here. This is the polarizability which we obtained here in the previous sessions. You can basically compute the scattered intensity to be equivalent to this particular thing, where this is almost like a constant term. Obviously, it depends upon the frequency and the distance. This is the actual term which is frequency dependent, and it denotes its response. And then there is electric field square, light's electric field square, sine square theta. So it's just like in a polar coordinates. In the polar coordinates, you have r, theta, phi. Okay. So just like if you have a spherical system, then you are going to have, this is basically r, then this is theta, and if you project it down, then this is going to be your phi. Okay, so this is the polar coordinate system we are using here. So what does it mean? It means that the intensity is directly proportional to sine square theta. That means at theta equals to 90-degree, intensity is going to be maximum. And it's symmetric. Why is it symmetric? Because there is sine square theta. Otherwise, if we use minus 90-degree, that is basically at this particular point. This is minus 90-degree and this is 90 degrees. So it is going to be symmetrically homogeneously emanating from this particular dipole. Okay, because of the sine square theta. Because the sine square theta looks something like this. Okay, so it's going to have an equal amplitude, maximum amplitude at both of these theta. This is minus 90 degrees, this is 90 degrees. Okay, so there is no preferential direction because of the sine square theta. That's what I'm going to basically highlight here. So from this, what we basically see is that there is a stronger scattering near the resonance. So at omega equals to omega naught, there is stronger scattering. Okay, and let's say for higher omega, if you go for higher frequencies, or that in other words means shorter wavelengths, okay, then it's going to have a strong scattering effects. That is what basically this equation tells you. Okay, that means if you have, let's say, 400 nanometer wavelength and if you have 800 nanometer wavelength, this is going to scatter more. It's going to have a strong scattering intensity compared to that of this, just because of this lambda to the power 4 dependence. Basically, there is a omega 4, so intensity is directly proportional to omega to the power 4. That means it's directly proportional to, let's say, c to the power 4 divided by lambda to the power 4. That means it is inversely proportional to lambda to the power 4. Okay, I guess this is one of the questions in your assignment also. Okay, so scattered intensity is inversely proportional to the lambda to the power 4. Now that is one more basically the interesting point is about the blue sky. Why the sky appears blue? You know that because there are different gas molecules. Let's say there is some ozone molecules, there is O2, there is nitrogen, there are other reactive species in the atmosphere. And once the white light comes in, this is basically a white light, so the lowest of the wavelengths is basically it's 400 nanometers to 700 nanometers. So 400 nanometers is it's the lowest frequency or a lowest wavelength. That means it's the highest frequency. Okay, so it's going to scatter the most. It's going to scatter the most. But the scattering is non-resonant. It is not at resonance. Why? Because these particular molecules, let's say a nitrogen molecule, which is nitrogen molecule. Okay, let me denote it like this. If this is a nitrogen molecule, then you know that the size of this is less than 1 nanometers. Okay, so that means for them the resonant frequency is going to be large. Okay, so that is the same case with oxygen molecule. The size of these species is very small. Okay, as a result, there is the corresponding resonance frequency is going to be large in this particular case. So you have a non-resonant response, which is basically also broadband in nature. So it's just like a non-resonant, but it's broadband. Okay, so this width is larger. So 400 nanometer will be scattered. And similarly, if we talk about the clouds are made up of literally water droplets. And these water droplets are bigger in size. They are literally of the order of millimeters. It depends upon the water size. So they are bigger in size. Okay. And it appears that they scatter almost all of the wavelengths equally. Scatter all of the wavelengths equally. Okay. So that is why they appear to be white. And whenever, let's say, for example, the size of the particle is less than the wavelength, then at that particular phenomena, we say that is something related to Rayleigh scattering. Rayleigh scattering phenomena. Okay, there are different scatterings. Let's say Rayleigh scattering. There is something called as Brillouin scattering I have talked about in the previous slides. There is something called as Raman scattering. Okay, there is something called as Mie scattering. There are different scattering phenomena, and obviously they depend upon whether the process is elastic or whether the process is inelastic, whether the photon loses its energy in the interaction, or whether it gains energy, or whether it changes energy, and what happens to that particular energy scenario. So it depends upon those. So these are different scattering phenomena which you can have a look on. Okay, so now moving on to basically lecture 2, what professor has tried to cover is something called as quasi-static limit. Quasi-static limit. What is a quasi-static limit in the electromagnetic field theory or electromagnetic fields? And also we have tried to cover the plasmonic resonances. Plasmonic resonances. So if you write Maxwell's equation, you can basically write Maxwell's equation in the form of, let's say, this form, where kappa is basically the wave vector of the electromagnetic wave, and omega square over c square e. You can just neglect for a time being that this epsilon is a k dependent thing. Just consider this epsilon to be only a frequency dependent thing. Okay, that means, and it's irrelevant because epsilon as a k dependent thing is basically mostly relevant for very small sizes. Let's say sizes which are less than let's say 2 nanometers or 1 nanometer. I don't know why this is behaving weirdly today. So for very small sizes, small sizes. Okay, so we're going to take it as almost only dependent upon the frequency or the frequency of the light. So there are now two scenarios that arise from this particular picture. The one is if your incoming wave is transverse, That means you have a transverse electromagnetic wave. That means for the transverse wave, the k dot E product is going to be 0. For the transverse wave, the electromagnetic field, the electric field is basically perpendicular to the direction of the propagation. Let's say this is H field, then this is how it looks like. And then there is another scenario which is basically longitudinal wave, where the k vector is parallel to E. It almost looks like if this is E, then this is going to be Z. Then this is almost like a longitudinal electromagnetic wave. If we solve for this particular scenario, we get basically that k square is equivalent to epsilon omega square divided by c square. Okay, for the light. And you know for a metal that the dispersion is basically given by inside the metal, it's equivalent to 1 minus omega p square divided by omega square divided by c square, where this is basically epsilon times omega. Okay, this is for metal, inside the metal. When you use both of these two, what you get is that omega square is equivalent to omega p square plus c square k square. This is what you get, where this p, you know that this is basically the plasma frequency of the metal. Frequency of metal. And we have been talking about what happens to, let's say, the reflectivity versus the frequency, omega divided by omega p, that at this particular frequency, at omega equals to omega p, the reflectivity almost drops, and it behaves like a, for example, at omega equals to omega p, it starts to absorbing, and beyond it, it starts to transmit. So let's say the transmission will look like something like this. Okay, so we have talked about the plasma frequency a lot. And now if you plot this particular curve on a omega versus k plot, you know that if we draw it like this straight line, this is basically omega naught equals to ck naught. This is for light in vacuum, in space. Now what is going to happen is that this is going to look something like this. This is omega p, plasma frequency. Okay, so this is basically the plasmon dispersion. Okay, so now that is mostly the focus of it. Now another thing which we will not be discussing in this course, so not important for this course, is basically the longitudinal part of it. And once you get the longitudinal part of it, basically you get something called as bulk plasmons. And that is not important. These are something sometimes also called as volume plasmons. So that's what we are not going to cover this in this course. Let's, for example, let's for a time being ignore this particular part here. We're going to only mostly talk about this transverse electromagnetic transverse modes, or transverse part of it, transverse part of this. Okay. So now what we are going to see is that something called as, what is a quasi-static limit? Quasi-static limit. So it's just like an approximation, or it's just like the limit we use, and it's not always valid. Let me be honest. So what, according to it, let's say for example you have some particle, let's say it's a nanoparticle, and if you have an incoming electromagnetic wave, this is an electromagnetic wave, then what is going to happen is that you know that there will be some positive charges induced on it, some negative charges induced on this particular, let's say, nanoparticle, and it's almost going to behave like a dipole. There'll be positive charges on one side, there'll be negative charges on other side, and they are separated by some distance, let's say x, and the dipole moment is basically the electric field times the x, the electronic charge times the x. And this is going to switch the direction. This is going to go here, this is going to go here. It's going to go periodically. Why? Because the electromagnetic wave is periodically varying. Okay, so accordingly the signs are going to reverse. This is going to go here, this is going to go here, and accordingly it's going to oscillate. Now, so what is going to basically happen is that if you have the wavelength of this electromagnetic wave as lambda, and if you have the particle which is, let's say, much smaller, let's say this is the nanoparticle we're talking about, this is the nanoparticle, and let's say its size is d, and if the size of the d is much smaller than lambda, then what is going to happen is basically, this is the electric field, this particle is going to feel a constant electric field. Okay, it's not going to feel the variation as if because you see that around this, let's say the electric field is constant. So it's going to switch, but it's going to feel constant. It's going to be positive, it's going to be negative, but it's going to be positive depending upon the switching of the electric field. But it's going to feel a constant or uniform electric field from the electromagnetic wave. Now, what happens when it switches? There is a basically separation of the charges. That means there is a dipole induced. There's a dipole induced. I don't know why it's behaving weirdly today. So there is a dipole induced. So induced dipole is basically this is negative, this is positive, and induced dipole field is basically in this direction, and it keeps on switching. And you know that the electric field inside the metallic system is basically zero. Okay, so this is just the property of the metallic systems, and so you find that, let's say for example, E induced will be basically equivalent to minus E times the external electric field. Oh, what happens according to this? It will be equivalent to this thing. I'm talking about outside it, outside the metallic system, outside the metallic nanoparticle. Okay. Now what is going to happen? Let's say for example we talk about this nanoparticle. This is the nanoparticle, a metallic nanoparticle, a metallic metal nanoparticle. And let me draw the coordinate systems. Let me draw the coordinate systems. Let's talk about this is r. Let's say this is theta. Let's say this is phi. This projection here. So this is the spherical system we are talking about. And we have an incoming electromagnetic wave which is coming in this direction. Then what is basically going to happen is that if you solve for the charges, if you solve for what is the charge density that will be basically induced in this particular nanosphere, you just solve it using simple equations. You get the polarized or the charge density to be equivalent to 3 times epsilon 1 minus epsilon 2 divided by epsilon 1 plus 2 times epsilon 2 into E naught cos of theta. So this is the charge density you will be getting. Obviously, because there will be some charges induced on this, will be positive charges, there will be negative charges. Okay, so here we are treating the external permittivity as epsilon 2, into this metallic permittivity as epsilon 1. So this is the permittivity of the metal, and this is the permittivity of the dielectric. Dielectric, let's say it can be air, it can be, let's say, water, it can be, let's say, glass, so it can be all other things. Okay, so what is this thing? So this means the sigma, the polarized or the induced charges is basically proportional to cos theta. That means it will be maximum at these locations and it will be minimum at the poles. Why? Because the in this particular direction the theta is increasing. At this particular direction theta will be 90 degree. So at, let's say for example theta equals to 90 degrees, sigma polarized will be equivalent to 0. Okay, so there will be very few charge. So it's almost like negative, then it drops. It will be negative and then it drops. So it will be positive, positive, and then it drops. It will be positive, positive, and then it drops. So at the poles, almost this is almost equivalent to 0. So these are the charges along the electric field direction. So you see that sigma polarization along the polar direction reduces. But the interesting part about this thing is what happens when, let's say for example, epsilon 1 plus 2 times epsilon 2 tends to 0. So when this goes to 0, sigma polarization tends to infinity. That means it blows. So it's almost like again the resonance phenomena. So this is basically the resonance polarization response. Okay. So what is going to happen is that if you solve this particular thing, that epsilon metal plus 2 times epsilon dielectric equals to 0, you know that epsilon metal is 1 minus omega p square divided by omega square plus 2 times epsilon dielectric is equivalent to 0. So from this particular equation, you can also say that epsilon metallic is equivalent to 2 times minus 2 times epsilon dielectric. This is the condition for the resonance to happen. Okay, so that means if you, let's say let's considering this, if you say that epsilon dielectric is equivalent to 1, then you get 1 minus omega p square divided by omega square plus 2 equals to 0. That means you get omega is equivalent to omega p divided by square root of 3. This is basically the resonance frequency of the surface plasmon. So this is surface plasmon resonance frequency. So it is half, it's root 3 divided by root 3 times the plasma frequency of the metal. So that is the condition for the surface plasmon to exist over this particular metallic sphere, metallic nanoparticle we are talking about. Now what is going to happen is that something like this, for example, if we talk about this particular system here, so the electromagnetic wave is coming, and the electromagnetic wave is coming. This is the electromagnetic wave we are talking about, and it is going to induce charges. Let's say, for example, this is positive, then this is negative, and it's going to reverse. And you see that the induced charges are out of phase. So the charge density is out of phase with respect to the incoming electromagnetic wave, with respect to the driving field. Okay, so it is negative here, it's positive here. So if you, let's say, draw the sigma sp, it will be just like this: negative, then it will be positive, then it will be negative, it will be positive. While the electric field is basically just like this. It is I should say positive, negative, positive. So it's completely out of phase with respect to the for example, let me just take it. So if I cut it here, if I paste it here, so it is completely out of phase with respect to incoming electric field. So that is what we mean to say by out of phase. So now, what is the other thing we need to think about? So using this particular relation, basically, we can compute what if we are given, let's say, for example, the metallic permittivity and the or the dielectric permittivity, we can compute basically the resonance frequency for the surface plasmons to happen in terms of the plasma frequency. And plasma frequency, we know it can be computed from the, let's say, the electronic concentration, from the permittivity values and all other things, because we have seen it in the previous sessions. Now, if we move on to, let's say, for example, the size dependence in the lecture 3 of this particular week, we talked about the size dependence of plasmon resonance. Plasmon resonance. So in the size dependence, what we see is that mostly it is it is basically experimentally studied by using something called as dark field microscopy. It is opposite to that of what the microscopes you might have seen, because they are mostly light field microscopy, which basically see the smallest objects under the light. But in this case, because they are mostly seeing the reflected light, if you talk about the normal microscopes, so let's say you have a certain sample and then you irradiate some light on this particular sample and you are catching the reflected light. So this is your eye from the scope. So that is a normal microscope. But in the dark field microscopy, if let's say you have some certain substrate and you have nanoparticles of different sizes, you irradiate it with certain light and the reflected light goes and it's blocked, it's not used. What is used basically is some scattered light which comes out from these nanoparticles. So this is basically the light which is gathered, and this is the light you basically see, the scattered light. So the scattered light is collected and analyzed. And then there are certain techniques how you do the signal processing of this particular stuff. That is the actual concept. So let's say, for example, if you have each different, so let's say, for example, each nanoparticle is of different size, then what is going to happen is that they are going to have a different resonant wavelength or resonant frequency. Okay, so this will be marked as a different color in this dark field microscopy. So in the dark field microscopy, you have the, let's say, for example, the entire background is completely black, and in between you see the nanoparticles as, let's say, dots of different colors. You see dots of different colors, and they basically represent the, I should say, the nanoparticles. So it's a different concept altogether compared to that of your normal microscopy, and it also depends upon the shape. If you, let's say, for example, have a nanoparticle of different shapes, let's say circle, let's say of different shapes, triangle shape, then accordingly what is going to happen is that the resonant frequency of the scattered radiation, if we draw it versus the resonant wavelength, then it's going to shift accordingly. So it will be for, let's say, for example, this will be for sphere, this will be for this shape, this will be for triangular shape. So all are going to have a different resonant wavelength altogether. Okay. And what happens, let's say, for example, if you have among these nanoparticles, one of the nanoparticle, let's say, of the size d, let's say this is nanoparticle of size d diameter, and let's say d is much, much greater than the wavelength of light, then you know that your quasi-static limit is not going to hold, is not going to hold. Then what does it mean? Is it means that if you have the electric field coming like this is the positive of electric field, this is negative. Now you have the, let's say for example, the nanoparticle is of this size. So d is comparable to that of the wavelength of the light. Now it is going to face a electric field which is non-uniform, which is varying, just like this. It will be positive, it will be negative. It's not going to be uniformly distributed over this entire sphere now. So quasi-static limit breaks down. Okay. Now, what is going to happen is that how we are going to understand what happens with the size. Again, if we talk about, let's say, for example, there is basically a calculation from, let's say, that comes from me theory. Me scattering is another phenomena, but they are the similar analytical equations. So as per it, let's say, for example, if this is one of the nanoparticle, if this is another nanoparticle. So this is nanoparticle 2, this is nanoparticle 1. So let's say, for example, the size here is D1, the size here is D2, and obviously D2 is much greater than D1. So what happens is if the electromagnetic wave comes for both of these particles, then it's going to induce the charges on these nanoparticles. Similarly, it will be inducing charges on these nanoparticles, and they will be switching as per the switching of the electromagnetic wave. Okay, electromagnetic field. Now, what's going to happen? We see that as we go on increasing the diameter, as we go on, let's say for example, if we draw let's say for example scattered intensity versus the wavelength in nanometers, we see that as we go on increasing the diameter, the d, as the d goes on increasing, the omega r redshifts, or in other words, it shifts towards red wavelengths, that means higher wavelengths, red wavelengths, or in other words, higher wavelengths. So why does it happen? Well, we can understand this from the Lorentz oscillator model again, which is it's a classical model, but it's very powerful in order to understand most of the phenomena. There are few phenomena only which you can understand quantum mechanically. Most of these can be understood semi-classically or classically. Even this Lorentz model is very essential for understanding it. So I talked about, let's say, for example, you have smaller nanoparticle, you have a bigger nanoparticle. This is size D1, this is size D2. And what is going to happen is that, let's say, for example, you have a negative charge here, you have a positive charge here. Similarly, you have negative charge here, you have positive charge here. Let's denote this as a dipole now, and let's denote similarly this as a bigger dipole. So this x is larger now, so this x is similarly smaller. So let's say, for example, this is like an electron, and this is like a plus positive charge. Not electron, this is like a negative charge, and this is like an electron, positive charge. So let's say they are connected with spring, and here they are also connected with spring. Okay, so it's just like a larger spring which is stretched, and this is like a smaller spring. Okay, so in this case, what is going to happen is that because d is larger, so the restoring force is going to be less. Why? Because the k is going to be smaller. Because F is equivalent to minus k times x. Okay, so now what is going to happen if k is smaller? What does the k denote, by the way? The k is also the factor that governs the resonance frequency, because omega naught is equivalent to k under root k by m. So if k reduces, the omega naught reduces. So if omega naught reduces, that means it shifts to lower frequencies. What shifts to lower frequency? The scattered radiation. So lower frequency means it means redshift. That means to high wavelengths. So that is one of the reasons which you can understand. Similarly, for the opposite case, that can happen. Okay, so higher order, you can get redshift because of this increase in the size of this nanoparticle. So this is one of the reasons which you can understand by simple mass spring mass systems. Now you can have one more important thing is that is confinement of the electric field. Confinement of the, let's say for example, electric field. And in the confinement of the electric field, let's say for example, if you have a nanoparticle 1, 2, 3, and if you have an incoming electromagnetic wave, once if you solve the Maxwell's equation for this, you get electric field profile to be something like this, where these basically show the pink area show the intensity of the electromagnetic field. Similarly, you get the electric fields to be something like this. So this is just like a positive, positive, negative, negative. So what's going to basically happen is that if you have a nanoparticle, let me change the colors as a similar colors. So if you have a nanoparticle and if you have an incoming electric field, so it's going to be just like this outside. But here it's going to interact with this particular, and there are going to be more field lines now. Okay, because here you have negative charge, you have positive charge, and you know from a positive charge, electric field lines emanate. Oh no, not this. And on a negative charge, electric field lines terminate. So that is why the direction of the arrows and the density of these lines, more the lines are closer, they show the electric field strength. Okay, so electric field strength will be huge. Let's say this is the diameter of the nanoparticle, and let's say this is the, let's say for example, some capital D, where this capital D is basically the something called as scattering cross section. Okay, so this scattering cross section is greater than that of diameter. It indicates that for how much region it's going to influence the outside electric field. So you see that there is bending in the outside electric field. There's bending here, and all of the other fields, electric field lines away from this nanoparticles are going to be just like a flat uniform. Okay, so this is like the distribution. Now you have this scenario in all of these three cases. For this case, for this case, for a huge nanoparticle. So once you solve these electric field lines for all of the three cases, you are going to get a distribution just like this. This is like a quadruple distribution. This is like a dipole type distribution. This is also like a dipole distribution. So for this, these are like multiple, multiple poles, or this is like a quadrupole distribution. Okay, so what is going to basically happen now is that the loss parameter which you talked about in the denominator of the, let's say, omega naught square minus omega square plus I gamma omega, this loss parameter which we talked about in the equation for the polarizability also, this now becomes dependent. It's now a space dependent thing, and it's given by something like this, where the A is a parameter which is mostly a scattering. It's a scattering mechanism dependent parameter. Okay, and the VF is basically the Fermi velocity. Fermi velocity is basically the velocity of electrons near the Fermi level. So because if you talk about the metal, so for the metal, if this is the EK diagram of the metal, and this is the Fermi energy. So up to the Fermi energy, electrons are filled, and now the electron is, let's say, here. The velocity of that particular electron at this particular level is basically the Fermi velocity. Okay, and this R naught is basically it's a distance parameter. So at larger R size, effects are going to be so if for example R is large, so size effects are going to be insignificant. This is only significant at smaller R. Okay. So now lecture 4, what you talked about is tuning of plasmon resonances. Tuning of plasmon resonances. How are you going to tune this plasmon resonance now? Now you have two things. Just give me a moment. Now you have two things. The first thing is either you can tune the optical constants, that includes also the epsilon or the refractive index or the permeability as well, or you can either tune the shape and size of the nanoparticles. Those are the two things which you can change. Either your nanoparticle can be just like this, or it can be just like this, or it can be of different shape and sizes. So accordingly, you are going to tune the resonance frequency, resonance wavelength, resonance frequency. You're going to change. So now, if you have the control over the shape and the size of the nanoparticle, your resonance frequencies are going to be different. That's what we basically saw. And we also saw that the sigma polarized is basically something twice epsilon, epsilon 1 minus epsilon 2 divided by epsilon 1 plus 2 times epsilon 2. So this is basically epsilon metal, this is epsilon dielectric. And accordingly, if you tune the one of these two things, you're going to tune this sigma SP, and accordingly, you're going to tune the electric fields, which are going to be inside this particular system. Why? This is basically the induced charges. Let's say this is negative, this is positive. So these are the surface plasmon charges, which are basically induced by the incoming electric field. Okay. Now, if you know sigma SP, then you can compute what will be the distribution of electric field. How you can do that? You can just simply solve the Poisson equation, which is dou, let's say dou E over dou X in one of the dimension. That will be sigma SP divided by epsilon. Okay. So this is the charge density. If you know this, if you know its distribution, you can compute the electric field. You can just integrate it sigma sp divided by epsilon into dx, let's say from x1 to x2. Now, obviously, you're doing it in spherical coordinates, so you need to have dou E over dou R, which is sigma sp over epsilon, and you need to integrate it in spherical system. Okay, so that is the basically you need to, how you need to solve it. Now, once you do it, you can basically again then compute something called a charge density. Not charge density, you have already have charge density. So let's say you have charge density, you computed the electric field profile or distribution inside the nano, or electric field distribution over the nanoparticle due to electromagnetic wave. I don't know why it's feeling weirdly. Electromagnetic wave. And if you have this, you can compute the current density. How you can compute the current? You know that J is equivalent to NQ mu times E. You can write it as this thing as sigma E. So J it will be, so current density will be equal to sigma times the electric field. So this is just like something, it's just like an Ohm's law, something called as microscopic Ohm's law. Okay. Now what is going to happen? This is the particular distribution of the let me cut this page here. Let me paste it here. So this is the particular distribution of for surface plasmon resonances of different dimers. Dimers, let's say for example, if you have a single shape of this nanoparticle as this, and then you have a nanoparticle something like these, and the red area is basically showing in this first plot. The red area is showing the intensity of the electromagnetic field. So it's higher at the both of these two ends. But if you see here in this particular thing, it is confined. Here it's confined. Okay. And here it's also confined. That means you can confine the electromagnetic field between these two dimers. Okay. Now, if you know the electric field, you can compute the current density. That is basically this particular thing. This is the second plot. This is showing the current density, and the third is basically showing the sigma. So you can go back and forth because you know that dou E over dou X is equivalent to sigma over epsilon. Let's say for example, it's equal to rho over epsilon. The, this is basically the normal Poisson equation. And if you know this, you can pretty much integrate it to get this particular electric field, or you can, if you have electric field, you can just differentiate it and you get this particular charge profile. Okay. So now what is going to happen? These are different current density profiles, electric field profiles. So for this, for example, you see that electric field is completely confined inside this particular diameter. And it is the important thing because if you can confine the electric field, so it almost acts like now a guide. So it can confine the electric field in a very localized manner. So here the confinement is goes on increasing. And you can see that how the charge density behaves. It almost behaves like this. That means if you have, let's say, a step-like thing, you can just basically take a derivative of it, and you get almost like a this type of charge density. Where this is positive, this is negative. Okay. So if this is electric field, then this is dou electric field over some dou x. This will be basically the sigma. It will be basically sigma over epsilon. So that is basically what I wanted to tell you, how you can basically go back and forth. And now, what else is there? Let's say, for example, if we talk about now something called as plasmon hybridization. Plasmon hybridization. Hybridization. This is just like the concept similar to what happens in the hybridization of different molecular orbitals. They just hybridize, let's say, for example, form the sp3 hybrid orbitals, sp2, sp3 hybrid orbitals, and that is the similar concept. Let's say, for example, if you have a sphere, let's say, for example, you have a spherical nanoparticle. What is going to happen if you just make it into a ring? Okay, there's a cavity in the middle, and you're going to form a ring. What is going to happen? So what is going to happen is basically now you're going to have a two resonant modes. Two resonant modes. Okay, earlier let's say the resonant frequency for this was omega R1, the resonant frequency for this is omega R2. Now for this it will be having two resonant modes. The first one, let's say for example, this is the first one. This is the first one is basically represented as omega plus. The second one is represented as omega minus. Okay, so this one is having a frequency, lower frequency. Okay, and it's called as bonding or symmetric mode. I'll talk about why it's called as so. And this is called as anti-bonding or asymmetric mode. Why is it happening only at these points? Okay, so what is going to basically happen is that once you, for example, there will be charge distributions just like in the bonding part, there can be charge distribution negative on the outer edge, positive here, similarly positive on this inner edge, negative here. So you can see that overall dipole field or the dipole moment will be negative overall here, positive in this direction. So the overall dipole field will be like this, and overall induced field will be in this direction because they are adding up each other because the negative is on one side and the positive is on other side. So it's almost symmetric around this particular point. Now for the other end, if you have, let's say, for example, negative on the outer edge, positive on this edge, and you have negative on this edge, positive on this edge, then it's anti-symmetric. It's not, the overall dipole moment is not going to be huge. The net dipole moment is going to be reduced. So it will reduce the net dipole moment, and as a result of which the net effective coupling with the free space is going to reduce. So the net effective coupling is going to reduce. Okay, why is it happening here? Net coupling going to reduce. Okay, so in this particular case, the net dipole moment is going to increase. That means what is going to happen is that it is going to radiate. And once it radiates, there will be, because it's going to be just like this, oscillating back and forth, is going to radiate. Once it radiates, there will be radiative losses. And once there are radiative losses, I mean, what is going to basically happen is that it's going to be losing its overall energy. Okay. So now what is basically going to happen? This is basically the scenario. So if you have a sphere, you can just form a, let's say, a nano shell of two different configurations, and this is basically the anti-symmetric, and this is the symmetric mode or symmetric configuration. It's just like atomic orbitals. You have the bonding and anti-bonding orbital. So if you, let's say, for example, draw the frequency versus the diameter of these shells. So as you go on reducing the diameter, You can have either antisymmetric mode or you can have symmetric mode. Okay, and this is having the larger frequency. The antisymmetric is having the larger energy. Symmetric is having the lower energy, and antisymmetric is mostly, this is not usually seen, not usually seen, and usually this is obviously obtained. So that means you mostly obtain the red shifting. Why? Because the frequency reduces. That means lambda increases towards the higher wavelength, and you get a red shift. Once you make these configuration change, as you go from this to, let's say, for example, these two different configurations. Okay, so now what are the real world applications of these photovoltaics? The professor has definitely covered the real world applications are thin film photovoltaics in order to increase, let's say, the efficiency of the solar cells. For the solar cells, you can basically now concentrate electric incoming light, or you can even couple electromagnetic light with the solar cell in order to increase the efficiency. You can have molecular diagnostics, basically the sensing purpose, where you can, why is it being weirdly here? It can be used for sensing purpose. It can be used for sensing purpose where you can tune the resonant frequency or the resonant wavelength as per the whatever the molecules you use over the surface. Just like if you have a nanoparticle, and if some molecules are coming in contact with the nanoparticle, then they're going to tune the resonant frequency. They're going to tune the resonant wavelength, and accordingly, you can get a shift in those things that will give you the indication of what are the different annihilates, different molecules present over its surface. Another is photothermal cancer therapy and plasmonic color filters. So these are the different examples. You can go through them. Now, what we are going to see is that there is something called a surface plasmon polariton. Now, what is a surface plasmon polariton? So it's a collective charge oscillation at conductor-insulator interface. Now, it does not only happen at a metallic sheet. You need to have, let's say, for example, metal. You need to have a dielectric, and there is going to be excitation of something called as surface plasmon polaritons at this particular interface between the metal and the dielectric. And when it's going to happen, it is going to happen when certain conditions are fulfilled. What are those conditions? That's what we are going to study. So surface plasmon is the surface plasmon we talked about. Now this is the polariton part. So it's like coupling of surface plasmons and electromagnetic waves. So this indicates coupling of surface plasmons and electromagnetic waves. Okay, so that is what basically the polariton means. There can be also something called as phonon polariton. There can be magnons. Other things can also couple with it. Okay, these are just the couplings. So now what they can do is that they can be used to enhance or transmit the certain electromagnetic energy in a certain direction, and they can hence act like an optical waveguide. This is like just like an these are the surface plasmon polaritons, and they can transmit the signal in certain one direction. So it's just like the electric plus optical combination, and they can be used to make, let's say, for example, waveguides. They can be used to make all sorts of uh, certain things where you can propagate the signal, and they are having a huge research domain right now. They are hot topics which are basically being pursued in different parts of the world. So now what we see is that, let's say, for example, if we have, if we see, for example, if we go on reducing the thickness of the film, the reflectance is going to behave something like this. You know that this particular frequency is the plasma frequency. Beyond it, you will have this particular behavior. Above it, you are going to have a different behavior. Okay, now let me just draw. Let's say, for example, you have a dielectric. You have a dielectric, and you have a metal. And for this, the permittivity is epsilon d. The permittivity is epsilon m. And if you have an incoming electromagnetic wave, electromagnetic wave, Then let's say, for example, epsilon d is greater than 0, epsilon m is less than 0. Okay, so now the electromagnetic field is coming, and when you draw the wave vectors of wave vectors of electromagnetic wave, in the dielectric it will be Kd, in the metal it will be Km. Kd will be Kx, y will be 0, and Kz will be minus Kz. So we are choosing the coordinate system as z, x, and this is y. Okay, so so what is going to happen in the metal? It will be Kx 0 minus Kz. So let's say this is K1z, this is K2z. These are just the coordinates of the wave vector. Now, if you solve for the, let's say, conservation of wave vectors. How is it here? I write this here? Wave vectors. Now, what is going to happen is basically you can write kx square plus k2z square will be equivalent to omega square by c square, this thing. Okay, how does it come up? It's just the conservation of these, that overall kx square plus kz square should be equivalent to that in the should be equivalent to n square divided by into omega square divided by c square, where this n square is basically epsilon metal. Okay, and now you can rewrite it in the form of k2z square is equivalent to epsilon m is equivalent to, let's say, for example, epsilon m square minus kx square. What's happening? That means if, let's say, for example, epsilon m becomes negative, k2z square becomes negative. That means it becomes imaginary. That means when it becomes imaginary, the light cannot penetrate into the metal. So what does this imaginary mean? It means losses, lossy terms. We have talked about it a lot, many times. Because refractive index is n equals to n naught plus I kappa. Okay, and this kappa is basically related to the absorption coefficient. This is kappa. This is not k. This is kappa. And now what is going to happen? Let's say, for example, when epsilon m is less than 0, that means it's negative. Let's say, for example, if we have omega less than omega plasma frequency, the plasma frequency. So you will see if you draw epsilon versus the omega, you're going to see a sign change at this particular omega equals to omega p. That means beyond this, the epsilon will be less than 0. Above this, the epsilon will be greater than 0. So that is what basically it means. Now, what is going to happen? Let's say, for example, let me show you a good example of this. If you, for example, if let's say we take again, this is the dielectric, this is the metal. So you might have seen that if you go on solving the Maxwell's equation now, you are going to treat the incoming field as like this. This is the electric field, this is the H field, and this is the Z direction. And now when you solve, let's say, for example, for two different modes, you solve for TE mode, you solve for TM mode. This is a little bit dry because it's going to involve mathematics, and for those who don't enjoy mathematics, it's going to be dry for them. So for the TE mode, you know that the electric field component is perpendicular to the direction of the propagation. So that means only EY component is there. So let's say this is Z, this is X. Okay, then this is epsilon D, epsilon M. This is metal. Similarly for TM mode, only HY component is going to be there. Okay, so this is epsilon D, epsilon M, and this is Z equals to 0 line. Let's say this is Z equals to 0 line. So if we write in medium 1, that means inside dielectric, we can write basically the H1Y component to be equivalent to H1 e to the power I k x x into e to the power minus k1 z into z. But this is the decaying part, this is the oscillating or the propagating part. Just because it's imaginary, it is more imaginary, it's basically oscillating. This is not having any imaginary, this is decaying. This e to the power minus x like term, e to the power minus z. Okay, similarly you can write h2y to be equivalent to, in medium 2 you can write it to be equivalent to h2 e to the power I k x x into e to the power k 2z into z. Why the negative sign is not here? Because we are moving in the downward direction. So it's just like an evanescent wave, evanescent decay. That is the same thing as decay, and this is now propagating in x direction. Now, what you have to do is that you have to solve del cross H is equal to mu naught J plus dou D over dou T. Let's consider this to be 0 for the time being. Then this particular term is going to give you minus I omega epsilon E. If you consider the fields to be harmonically varying, that means you consider them to be like a sine wave or a cosine wave. Then you get dou D by dou T to be equivalent to minus I omega epsilon times electric field. And when you write this curl of magnetic field in terms of its the curl, which is dou by dou x, dou by dou y, dou by dou z, 0, hy, 0. You're going to solve this. I guess this has been covered in the sessions. What you're going to get, you're going to get E1 and you're going to get E2. And using the boundary conditions, what are the boundary conditions for it? The boundary conditions are that h1y at z equals to 0 is equivalent to h2y at z equals to 0. That means if this is epsilon d, this is epsilon metal, and this is z equals to 0, then at this particular interface, the magnetic field components are going to be equal in this particular direction. Okay, basically the perpendicular components of this field. So h1 will be equivalent to h2. Why is it behaving so irritating here? So, and the second boundary condition is that E parallel is to be continuous. That means the parallel component at this particular end is equivalent to the parallel component at this particular end. Okay. And when you use this, you get K1Z divided by K1Z divided by K2Z is equivalent to minus epsilon D divided by epsilon M. This is also one of the questions you have in your assignments. You get this condition for a propagating surface wave, that the wave vectors in first along the z divided by wave vector in second medium along the z should be equivalent to minus epsilon d divided by epsilon m. So only then you can have a surface wave. Okay, that means, what does it mean? It means that epsilon d and epsilon m should have opposite signs. Okay, only then both of them will be positive. K1z will be positive and K2z will be positive. What happens if they are negative? That is what basically if you see here. Okay, only then these both of them are going to be negative. Oh, sorry, positive. So now if we combine K1z and K2z, we can write basically Kx square to be equivalent to epsilon d epsilon m divided by epsilon d plus epsilon m, K naught square. So you can write kx to be equivalent to square root of epsilon d epsilon m divided by epsilon d plus epsilon m k naught square, where k naught is the free space propagation, or the free space wave vector, and this gives us the dispersion for surface plasmon polariton. Now is the essential part of the discussion. What is happening? Now what is happening is that if you have omega versus kx, earlier for the free space, omega naught is equivalent to ck naught. This is for the free space. But what is going to happen? There's going to be a behavior something like this at omega p divided by square root of 2. Okay. So now from this equation also you can see that if epsilon d plus epsilon m is equivalent to 0, that means epsilon d equals to minus epsilon m, and you can just put it into the epsilon metal is basically 1 minus omega p square divided by omega square, and you can use it and you get omega to be equivalent to omega p divided by square root of 2. This is the condition for surface plasmon polariton resonance. Okay, so just give me a moment, I'll just back. So now what we are going to see, let's change this. So we are going to see now what are basically these surface plasmon polaritons. And this is the fundamental equation which you need to understand in order to understand the dispersion of the surface plasmon polaritons. Now, for example, if you have, let's say, for example, you have kx to be equivalent to k naught square root of epsilon d epsilon m divided by epsilon d plus epsilon m. And you know that kx square plus kz square is equivalent to k naught square. We're talking about this particular system where this is dielectric, this is metal, and this is epsilon metal, this is epsilon dielectric. And you have an electromagnetic wave coming in this place with the wave vector k naught. Okay, so and this is x direction, this is z direction, this is y direction. That is the scenario we're talking about. So from this equation, you see that if epsilon d plus epsilon m is equivalent to 0, that means epsilon d equals to minus epsilon m. You saw that the resonance frequency of the surface plasma polariton will be equivalent to plasma frequency divided by square root of 2. This is the condition for SPP to occur. And if you have, let's say, for example, frequency much less than the plasma frequency, then what is going to happen? Because for the metal, you can write it as from the Drude model, you can write it as this thing. So if frequency is much less than the plasma frequency, then epsilon m is much less than 0. That means it's negative. That means kx will be approximately then k naught times square root of epsilon d. Okay, that is what it means. Now what does, for example, this particular equation tells you? It tells you because lambda naught is equivalent to 2 pi by k naught. This is the free space wavelength. This is the free space wavelength. And if you, for example, draw the dispersion, so the essential part is that we need to know how much smaller is the wave compared to that of the free space. So if you have the essential thing, what we need to know in the surface plasma polariton resonance is to know how small is the lambda compared to lambda naught. And that is what basically the ratio of kx by k naught is going to give you. So it's going to give you the lambda inside over the surface plasma polariton, the wavelength of the surface plasma polariton. This is going to give you the lambda for the free space. Okay, so you can write lambda surface plasma polariton to be 2 pi by kx times, let's say, k naught. You can write it as k naught. It's basically 2 pi by kx, not k naught. It's lambda surface plasma polariton is 2 pi by kx. You can multiply it by k naught. That means you can write it as 2 pi by k naught into k naught over kx. So this is for the free space. So you can write surface Plasmon Polariton to be equivalent to lambda naught k naught divided by kx. Therefore, you can write SPP lambda SPP divided by lambda naught to be equivalent to k naught by kx. Now, if you know the k naught by kx ratio, you can compute basically what is the wavelength of the surface Plasmon Polariton compared to that of the free space wavelength. Okay, so now what else is going to be important? Now, another few things that are going to be important is how you are going to excite these. There are different exciting configurations we will talk about in the maybe assignment problems. We will talk about the excitation of surface plasma polaritons. That is the only thing which is left, I guess. If I can see, yes. So let's move on to the questions. So this particular figure basically shows the essential why plasmonics is essential. So it covers basically it's essential because it covers the frequency of the photonics. You get the frequency of the photonics and you get the size scale of the electronics. That it covers the good things, good of both things. Okay. So that's why you want to go to the plasmonics. You can go to terahertz frequency, which you know that electronics cannot go because of the limitations. Okay. And what governs the frequency in the electronics? Let's say you have a MOSFET. This is the source, this is the drain, this is the gate. Then if the electron is going from this terminal to this terminal, and if the length is L, then basically there is certain time it takes, something called as transit time. So let's say tau is equivalent to length over velocity of the electron. So you can write it as frequency to be equivalent to velocity of electron divided by L. So this is basically the frequency at which the device works. Let's say it's something called as unity gain frequency or as well. So you cannot go on reducing the size even to a smaller and smaller and smaller. I should say you cannot keep reducing the distance between source and drain because there are some other effects which come into picture, extreme short channel effects, quantum mechanical effects. So that's why we are heading towards the limitations of the CMOS electronics. It's hitting the limits in terms of the frequency. Now that's why we are looking for the alternatives. One way is to go towards the plasmonics, where it can work at the frequency of the light and the terahertz frequency. And on the other hand, it can be basically made on chip. It can be made on chip. And you can have a size scale of the order of, let's say, nanometers. So this is very promising in today's technology. Let's now talk about some of the questions. So we're going to start the problems here. So for the question one, it is given that you have given a wave equation. The psi is just the wave equation, which is a e to the power I k y into e to the power minus kx times x for x greater than 0. So we are going to see that there are two parts in this. This is basically the propagating part I have been talking about. This is the decaying part, evanescent mode. Evanescent decaying part. So because that means if you have its distribution in x, then it's going to decay in x at this particular rate. And if it is in y, then it's going to oscillate in the y. That is basically the notion of what this wave represents. Okay, so the wave is propagating in y direction and its evanescent decay in x direction is the answer of this question. So for the second question, we are given a metallic sphere of, let's say, we are given a metallic sphere of radius 30 nanometers, and plasma frequency is the plasma frequency is omega p. It's embedded in a dielectric environment. Let's say this is a dielectric environment of permittivity 3. So this is epsilon m. The condition for excitation of localized surface plasmon resonance, that means LSPR, localized surface plasmon resonance, when the light of frequency is incident on a sphere. Some light is coming in with frequency omega. We need to find what is the condition for LSPR to happen. So we know that sigma sp, that will be induced charge density. We have computed it to be epsilon twice epsilon naught, epsilon metal minus epsilon dielectric divided by epsilon metal plus twice epsilon dielectric. That we have computed. Now what we can do, for the resonance to happen, epsilon metal plus twice epsilon dielectric should go to 0. And epsilon metal, we know it can be written as 1 minus omega plasma frequency square divided by omega square, light frequency square, plus 2 times epsilon dielectric equals to 0. We know epsilon dielectric, which is 3. So it is 1 minus omega p square divided by omega square plus 2 into 3, which is equal to 0. So you get, I guess this is 1 minus this thing plus 6. Are we doing right? Okay, so 2, 3, 6. How much is this? Oh, epsilon d is 3. That means you get, let me just confirm. Yeah, you get 6. And it should be around omega p square divided by omega square. You get approximately to be 7. So omega square is equivalent to, or omega is equivalent to omega p divided by root 7. So there is some problem, I guess, because none of the options is matching. So this should be the actual answer of this question. I'll still cross-check whether there is any other information given in this, because I don't see whether this particular can be used anywhere. So this is as simple as that. You use the epsilon metal from the Jude model, and you put the epsilon d to be 3, and that is as simple as that. Yeah, let me just cross-check it whether there is any issue with this question, because I can see there are 5 options given. I don't know why. Okay, we'll get back to this question. Let's say now we have question number 3. What is question number 3 saying is that it's about surface plasmon polariton. That means you have a dielectric, you have a metal, and it's always excited at a dielectric metal interface. It is not excited at this particular, because this does not follow the conditions for the surface plasmon polariton resonance. That means, let's say for example, if you have an incoming wave, which is, this is the H and this is the electric field, this is the incoming wave, then it will go here. This is the K incident, this is K reflected, this is K transmitted. The transmitted part will be, it will be just like exponentially decaying, so that this exponential decaying can couple with the surface plasma polariton, and it can go in this direction. So this is K surface plasma polariton, this particular direction. Now what is it saying? So this is epsilon dielectric, this is epsilon metal. If it undergoes surface phenomena with the wave equation, so the wave equation is given. You're given Hy equals to A e to the power I k x x e to the power minus k z z. That means this is z direction, this is x direction, this is y direction. That's why it is decaying exponentially in z, and it is oscillating in x direction. That is right. Which of the following is true of the permittivity? So we have to give the relation between the permittivities. What is the relation between epsilon d and epsilon m? So we showed that for SPP to occur, the kx, the wave vector in x direction, should be equivalent to free space wavelength, free space wave vector, epsilon m, epsilon d divided by epsilon m plus epsilon d. For the surface plasma polariton resonance to occur, the denominator should go to 0. That means epsilon m should be equivalent to minus epsilon d. That means both should have a negative signs. Okay, that means they should have opposite signs. That is the answer of this question. Okay, that also means that, because you know that lambda, that means the basically the kx should be greater than k naught. That means lambda should be less than lambda naught. The wavelength of SPP should be less than the free space wavelength. Now by how much? We also computed that lambda SPP divided by lambda naught should be equivalent to k naught divided by kx. This is the exact ratio for that. This is not asked, but we also computed that. You can also this maybe this might be asked in your exams, but this is having a similar relationship. Now what is the other question? Consider the light incident on two closely spaced metallic spheres. Such a system of particles supports two kinds of resonant modes, bonding and anti-bonding. So we have seen choose the correct option regarding the resonant mode. So we have seen that if we have two closely spaced metallic particles, it can have a bonding mode, it can have a non anti-bonding mode. That means if these are closely spaced metallic spheres, a charge can have a distribution like this, where there is a overall net electric field in this direction, so it enhances the dipole moment. So it enhances the dipole moment. Another configuration can be like this. This is negative, this is positive. So this can be negative, this can be positive. So it reduces the overall dipole moment. And because this is asymmetric around this point. This one is symmetric around this point. Okay. So this is asymmetric, this is anti-bonding, this is bonding, and this is symmetric. So which of the following we have to see? So we have to see that bonding resonance occurs when electric fields in two particles oscillate in phase with each other. This one is wrong because the bonding gives you the lower. You saw the graph of omega versus d. D is the size, so it goes like this. This is anti-bonding. This is bonding. So bonding always gives you lower frequency compared to that of anti-bonding. Anti-bonding generally results in higher energy state compared to bonding, and bonding bonding occurs when the electric field in two particles oscillate in phase. So this is the answer of this question. The electric field, yeah, that is the point basically. So when these oscillate in phase, the electric field of here is electric field of this outer particle. Let's say for example the two particles, they oscillate in phase, then it gives rise to the bonding modes. Okay, so that is basically from this configuration you can understand. Now question number 5. It's the simplest one. The phenomenon of sky appearing blue is due to Rayleigh scattering. When the size is much less than I should say the wavelength is much less than the size. Which of the following is correct? The sky is blue due to non-resonant scattering, and it has equal probability of forward and backward scattering. That means if these are the nitrogen atoms or oxygen atoms, because of the lower size, so basically this is not this is the size is lower of the order of, let's say, less than 1 nanometers. What's going to happen? The blue light is going to scatter the most, the higher wavelength, and it's non-resonant as we saw in the lectures. And it has equal probability of going backward and forward scatter. So it has equal probability of scattering in all the directions. So there is no preferential direction in this particular type of scattering. So that is what basically it means. Now this is the particular configuration of exciting the surface plasmon polariton, something called as Fleischmann configuration. There are many configurations. There is auto configuration also, and there is like grating configuration, which maybe there might be another question about it. Fleischmann configuration, Fleischmann configuration. Okay, so what does it say that if you have, let's say, a thin metallic film, this should be thin. That is the condition, first condition. It should be around, let's say, 10 to 20 nanometers, where the electromagnetic field can decay into it and can couple to it. This is like, let's say, the dielectric, epsilon d. What's going to happen? The electromagnetic wave comes in, it goes here, the one part goes reflected, other part goes outside the prism. So the part decays to the metallic side and excites the surface plasmon polaritons in this direction. That is basically what happens in case of Fleischmann configuration. Okay, and why does it happen? Because once the electromagnetic wave comes in, it has to be the transverse magnetic electromagnetic wave. So at this particular position, you can basically uh, divide it into two components, K perpendicular and K parallel. Okay, so now what is going to happen is that along the, let's say for example, along the, I should say, Z direction, it's going to have a decaying evanescent decay part. And if the metallic layer is very thick, then evanescent decay will just go here and it's not going to reach this particular end. There will be no excitation of surface plasma polariton in that case. That's why the layer thickness is going to be important, so that the evanescent decay mode can couple, the tunneling part of the electromagnetic wave can couple to this edge of the metallic sheet in order to excite the surface plasma polaritons on the surface. So that is the concept. So in other words, this will be the direction of the surface plasma polaritons. Surface plasma polaritons. Okay, it can be in this direction or it can be in this direction. That is basically the opposite of each other. And the possible scenario that looks, this is not possible because you cannot excite surface plasma polariton at this particular surface, at the interface between metal and dielectric. It has to be at the surface of the metal. Similarly, this is also not possible because it's showing two different surface plasmons generated on two different surfaces. This is also not possible because you cannot have a surface plasmon. It's weird. You cannot have it in this direction. So the only configuration that is supporting is that surface plasma flow like this over the surface, not at this interface, just at the surface of the metal. So the only option that matches is option B. Okay. Now we have another way of exciting surface plasmon polaritons. The another way is if you have electromagnetic wave, it can hit a grating. A grating is just like this structure, a repetitive arrangement of some certain structure, which has its own wave vector, which is basically the grating wave vector given by 2 pi divided by period of the grating. So this is the period of the grating. So it's just like a space. It has a spatial frequency. It has a spatial frequency of p. Okay. So now that is going to have an impact on the overall k. So the overall k will be kx plus minus m times g. So overall k SPP will be equivalent to the k in this direction and plus the k, the momentum, which is basically because of the spatial part of this grating. So just like if you have atoms, if this is a regular arrangement of atoms in a crystal, I'm talking about in a crystal, then these are also, let's say, periodic by A. Then also you write its spatial frequency, or you can write its spatial part, or you can even write its wave vector g to be equivalent to 2 pi divided by the lattice constant. That is basically what happens in the lattice. And you do all of those X-ray diffraction measurements, okay, where you conserve the particular wave vectors of the incoming X-ray. Then you have the wave vector of the lattice, which is a repetitive arrangement of the lattice cells. Okay, and then you have the similar conservation of the wave vector. That is basically the same scenario. What happens here? So overall wave vector of this will be given by kx plus minus m times the wave vector because of the grating. Okay, so this kx is basically the k parallel component of the electromagnetic wave. Because electromagnetic wave is coming here, it's going to have this k parallel component. Okay, and it's going to have, let's say for example, this is the electromagnetic wave coming, then this is the normal. It's going to you can basically divide it into two components. Okay, so this will be one component, this will be one component. This will be, let's say for example, this is theta, then this is k sine theta, this is k, then this is k cos theta. That means this is basically the parallel component, this is the perpendicular component. So overall k SPP will be equivalent to, because this is the direction of k SPP or kx, then it will be k parallel plus minus m times the wave vector of this particular uh, grating. Why this plus minus is because grating, you can take a grating in this direction because it's symmetric along any direction. You have grating along both of these directions. So these are two directions of the gratings. Okay, so it's going to give you the same thing. So it's just like the just I talked about the momentum conservation, nothing else. And the same thing happens in X-ray diffraction, same thing happens in the crystal lattice system, where you have the repetitive arrangement of the crystal atoms, and they act like almost like a grating for the electrons. That's why you have specific electron momentum values acceptable. That's why you have the electrons dispersion in the crystal lattice, which looks something like this, in the first Brillouin zone. That's what you talk about EK diagram in the for the electrons in the crystal. That is the same phenomena. So you can just correlate these two, all of these phenomena. This is happening with light. This is happening for the electrons. As simple as that. Now, question number 8, we have again discussed about it, that these are two spherical nanoparticles made up of metal. Both are made up of metal and are resonant at different wavelengths. So one is resonant at this wavelength. Let's say this is P1 and this is P2. Which of the following is true regarding the size of nanoparticles? We saw that if we go on, what is happening is that if we go on increasing the size of the nanoparticle, the restoring force is going to reduce. The restoring force is also going to reduce. K is going to reduce. That means omega naught is going to reduce. That means lambda is going to increase. That means it will be high wavelength, at high wavelength. Similarly, if we reduce the size, then K increases, omega naught increases, lambda decreases. That means it's for the low wavelength. So that means it will be having resonance at low wavelength. That means low wavelength resonance for the smaller particle. That means P1 is smaller than P2. That means P1 is smaller than P2. So that means P2 is greater than P2 has a larger diameter than that of P1. So that is what basically we talked about. That is as simple as that. This is just like this is smaller particle, this is bigger particle, this is negative, this is positive. So you have a negative, positive charge. This is like a spring. This is negative, this is positive. So this is negative charge, this is positive, and this is like a spring. And accordingly, you can see what is going to happen to the restoring forces in both of these cases, depending upon the sizes. Now, question number 9. Question number 9 says that you have two beams. One is 800 nanometer, another is 400 nanometer, and you are considering the Rayleigh scattering. So compare the scattered intensity of both of these, and how many times stronger is the scattering intensity for 400 compared to that of the 800. So we need to see, because both of them are going to be, let's say, scattered from certain particle, is going to scatter from certain particle. Okay, now you saw that the scattered intensity is basically directly proportional to the frequency to the power 4. That means it's proportional to 1 over inversely proportional to the wavelengths to the power 4. That means for scattered intensity for, let's say, 400 nanometer divided by scattered intensity for 800 nanometer, that will be equivalent to lambda 800 nanometer square divided by lambda 400 nanometer square. That means it's basically 800 divided by 400 square. So it's 2, not square, it's 4 to the power 4. So it's to the power 4, so it's 16. So that means I for 400 nanometer is 16 times I for 800 nanometer. That is what basically we talked about. That for a lower wavelength, there will be huge scattering, the Rayleigh scattering. And that's why for the 400 nanometer, the scattering intensity is 16 times stronger compared to that of the 800 nanometers. Now the final question, again, we discuss this particular thing, that this is basically a dielectric metal interface. And if you want to excite the surface plasma polariton, let's say KSSP, SPP, then what is the condition for the epsilon dielectric and epsilon metal? We saw that the condition is that the K in the dielectric divided by K in the metal should be equivalent to negative times the K epsilon dielectric divided by epsilon metal. That means epsilon dielectric and epsilon metal should have opposite sign so that Kd and Km are positive. Okay, so that is the only part which is matching. This is basically what we solved in the upcoming in the previous slides. I guess I showed it here. Where was it? Yes, here. So it's upon solving the Maxwell's equation, you get this particular condition. Okay. So the condition for surface plasmon is the condition for surface plasmons to occur is basically this thing. And you can also see that epsilon d and epsilon m have to have opposite signs. Why they have to have opposite signs? Because you saw that kx, that means k SPP is equivalent to kx, which is equivalent to k naught under root of epsilon m epsilon d divided by epsilon m plus epsilon d. So for the epsilon m plus epsilon d to go to 0, epsilon m should be equivalent to negative times epsilon d. That is what basically the condition also tells you. But they should be opposite. But this ratio you will also get similarly. Okay, so that's about this session today. I hope I was able to cover most of the things, but there are a lot of things which were covered in this particular week. So we are done with today's session, and I hope to see you in the next week at the same time. Okay, thank you.